Today's webinar is on using Norsand Constitutive model for deformation and stability analysis problem. I'm Alireza. I'm with Rocscience, and today I'm honored and pleased that we have Dr. Ghafghazi with us. Mason is a dear friend of mine, and he's a professor at University of Toronto and the expert on the subject. So Rocscience, we are a world leader in developing innovative 2D and 3D software for civil, mining, and geotechnical applications. For more than 25 years, we have built geotechnical tools used by over 10,000 users around the world, and we are dedicated to deliver industry-leading software programs, exceptional customer service, and unparalleled technical expertise that engineers can rely on. So the image that you are seeing on the right is the Rocscience office, and it's just 10 minutes walk from University of Toronto. With that, I'll pass the presentation to Mason.
Hello, everyone. I'm going to talk about background and calibration Norsand fairly briefly. I'll then pass it back to Alireza to continue to show you a model of a tailings dam. So on background, what is Norsand? What's good about it? What's not so good about it? And kind of introducing its parameters. Norsand was, of course, made by Mike Jeffries in 1993, and then there has been quite a few updates after that, including the paper I'm referencing. And of course, you can use the Bean and Jeffries book on liquefaction to find all of the background information on Norsand. And Norsand is an expansion of CAM-CLAY. CAM-CLAY was a critical state model, meaning that if you shear soil long enough in one direction, it will end up at the critical state. And it was based on two fundamental assumptions. One is that friction is the main mode of dissipation of energy or work as grains rub against each other. And the direction of flow is perpendicular to the yield surface. This is a pretty straightforward thing if you get deep into it, but we call it normality. It's one of those assumptions that shows up in a lot of models. And but CAM-CLAY, as you can tell from its name, is a model that's targeting clays. When it came to sands, even though you can try to fit CAM-CLAY to some sand, loose ones usually, you cannot capture the wide range of behaviors that sands have, because you can get sands loose and dense and everything in between. They have different mobilized friction angles, and CAM-CLAY is not quite capable of capturing those. So what Mike Jeffries did, he introduced the idea of state parameter into CAM-CLAY that enables you to define all sorts of densities, void ratios, and then he untangled the yield surface from the critical state, and it gave it the ability to change shape by making it a function of the mobilized friction angle, or the image friction ratio, which is equivalent to that. And of course, there are other bells and whistles. There's a limit on dilatancy. There's N, a parameter we'll talk about, to store energy during plastic straining. And there are other softening parameters in order to capture cyclic behavior as well. I'm now going to switch to some of these videos that one of my students made, just so you guys understand how Norsand operates. Top left is the one I want you guys to focus on. This is the stress path, the deviation stress plotted versus mean effective stress. And on the right, you have deviator stress versus axial strain. These are standard measurements out of tests. You have pore pressure, and then you have on the left, the void ratio versus log P with the critical state line drawn. So starting from the most basic one, this dashed line is the mobilized friction angle, starts pretty close to the critical state, ends up at the critical state. As the yield surface expands, you get expected behavior in the deviator stress, volumetric strain is contracting, and eventually everything reaches the critical state. And that's where you stay, everything plateaus. Dense behavior captured the same way. This time the mobilized friction angle has a more pronounced effect. and what you get is the sample's dilating. The yield surface expands at first, and then it contracts, and that's how you get a peak, and then towards a residual value there. And if we look at the dense undrained behavior again, you can see this time we're looking at excess pore pressure, a bit of contraction at first, and then dilation is what you get, all with the exact same set of parameters and the same assumptions of the model. And finally, this is the one a lot of us are interested in. This is your typical static liquefaction behavior, and which happens in a loose specimen as it moves towards the critical state line with pore pressures rising, and you get a peak undrained strength and then towards a residual strength out of the model. So what's good about Norsand is that it's got not too many parameters, just 8. 7 out of these 8 are basic properties of the material you can calibrate from triaxial tests. You don't need to understand Norsand or even have access to it to calibrate. You just process your lab data and get those parameters. One of them, H, which is the hardening parameter, is what you need to, once you set the others, to fit to Norsand in order to determine. And it's implemented in a lot of finite element, finite difference packages, including RS2 and RS3, of course, and RS data if you wanted to calibrate Norsand. Norsand works very well in monotonic loading for drained and undrained conditions. Triaxial is very, very good. Simple shear is good. And it works well for constant shear monotonic loading, which makes a lot of tailings engineers worried. And because it has state parameter at the core of it, you can basically get the state parameter from CPT data, again, for example, in tailings, and plug it into your model, and that's all you need after you've calibrated your model. Norsand is not meant to do cyclic. Mike Jeffries has done cyclic with it. It does have the parameters, but it wasn't born that way. So cyclic loading is something that it sometimes struggles with, needs a bit of expert input and calibration to do well. Norsand's parameters are elasticity parameters, elastic modulus, G, and nu, the Poisson's ratio. You got the critical state parameters, and then you have 2 parameters, dilatancy. You can get these 2 on dilatancy. You can get these 2 from triaxial test data, and the last one which needed fitting to the results is the hardening parameter H. Here I have a range of these parameters. Tailings tend to be on the higher side of some of these parameters, such as the friction ratio M or chi, the dilatancy parameter, and they are sometimes more compressible, so you get higher lambda values. That's the slope of the critical state line. For elasticity, you put it in as the elastic modulus G or the elastic rigidity I sub R, which is just the ratio of G to your initial mean effective stress. Obviously, you measure this from Bender elements in lab, and you can measure it from shear wave velocity in the field. You need shear wave velocity and G in order to interpret CPT properly anyways, if you're getting the state parameter. So you might as well put that into Norsand. It matters more for undrained models than drained models. And G is a function of the void ratio and mean effective stress. When you're dealing with modeling Norsand, make sure you understand how this parameter is implemented in the model. Sometimes it's a constant, sometimes it remains a function of void ratio and P prime. Poisson's ratio is the little brother to all elasticity moduli. It's usually assumed, I always assume it's 0.2. It doesn't affect most models much. If you measure it from V pressure wave to S wave velocities in field, you usually get about 0.3. It's not something you need to be too concerned about in most cases. Then you have the critical state friction ratio M. This is equivalent to the constant volume friction angle. Alireza will cover this. And it's basically the ratio of deviator stress to mean stress once you reach critical state. Then you have the critical state line. I usually use the semi-logarithmic idealization with gamma being the intercept and lambda being the slope. You can have different shapes as well. It doesn't matter. Norsand can take anyone in. And then you have the state parameter also defined, which is the difference between your current void ratio and the void ratio at the critical state. Your dilatancy parameter chi is there's a bit of equations here. I'm sure most of you are already familiar with this. This is just how you process your drain traxial data and dense specimens. So you need a couple of these at least to calibrate chi. And you calculate basically the ratio of increments of your volumetric strain to your deviator strain. It has to be the plastic component, doesn't really affect things much once you're near the peak, which is where you should be looking at this. So you find your maximum dilatancy and plot it against the state parameter at that point. That's basically when your dense specimen gets to peak strength. And you plot a few of these and you fit a line to them, and that's how you get chi. I'll show you an example in a couple of minutes. Then you have the plastic coupling parameter N. You would get it the same way you get M, the friction ratio, so it doesn't really require extra work or extra data. And to understand it, if you think of dilation as going uphill, as a sample is expanding, it's fighting the confining stress, and it's kind of like going uphill or going upstairs. N is like the slope, so that's how it stores energy as well. It's like pushing a block up a slope, if you want to think of it that way. And then you get to the only parameter that needs fitting to data, and that's H, the hardening parameter. This controls how the size of the yield surface changes. And once you calibrate to a few tests, you'll see that it's probably a function of the state parameter. So you fit something like a line to that, and that's how these H naught and H psi show up. They're really not additional parameters. That's just how you make one of these functions a function of your density. I'm going to show you an example calibration from 11 tests that I ran when I was a PhD student some 15 years ago on Fraser River sand. This is sand from Vancouver, British Columbia, and Canada. And these were mostly drain tests, as they're supposed to be, some undrained tests in there. The minimum number for being able to calibrate Norsand is about 6 with very careful planning and a bit of luck. But 10, 11 is a good number. It really matters that you do and get high quality traxial data with good measurements of void ratio. And here are a few references if you wanted to look them up for procedures for performing these traxial tests. Now, calibration, we start from the critical state. I'm going to skip elasticity because I'm sure you're all familiar with it. We're going to calibrate to the critical state line, then the critical state friction ratio and N, they are calibrated together. Chi is after that, and then the last one is the hardening parameter. So the first one is getting the critical state line. Basically, you want to shear your samples to large strains, and once you get as far as you can, whether to the limits of your equipment or because you're seeing shear banding and the sample's falling apart, you stop, you freeze the sample, you make sure you get the correct void ratio, and at that point, you plot this void ratio against the mean stress at the end of the test. It's important to identify what the sample was doing at that point. I've separated my samples into ones that were at critical state, no volume change, no excess pore water pressure change, no change in deviator stress, and ones that were still dilating or contracting. And then I drew a line by putting a lot of weight on the ones that were at critical state. And I made sure that the circles, which are samples that are still contracting, fall above the line, and the triangles that are samples that are still dilating fall below the line as they're supposed to be. And that's how I identified this particular line. And you can see gamma and lambda in that equation box up there. The next one is determining M and N. You can basically, you plot the minimum dilatancy. This was not the minimum, dilatancy, which is the ratio of increments of your volumetric strain to the deviator strain against the stress ratio, eta. The vertical axis here is Q divided by P. It's the deviator stress, or delta sigma. It's basically your vertical load divided by the mean stress at the same time. I like plotting the entire path and then identifying the peaks. Those red points are the peaks, and you fit a line to this, and that's how you get both M and N in this case. But plotting the entire path kind of helps you identify those peaks and see what's going on. Do not go with a blind selection of the peaks, because you're dividing very small, those increments of strain that you're dividing by each other are very small numbers, and you don't want your numerical kind of instability to affect your choice. Sometimes I run a moving average on this if I need to smooth the data a bit, but it's always good to plot the path and pick those points visually. The next one is chi, very similar. What was your horizontal axis in the previous plot is now the vertical axis, and the horizontal axis here is the state parameter at the position you're at. And again, you get this path, and I identify these points, and I picked a chi of 3.2 in this case. You could lower it a bit. It's a matter of opinion at that point. And once you have all of these, you can basically go to this VBA that is provided with the Bean and Jeffries book, or you can use RSData. RSData is a bit cleaner. I just didn't have the license on this computer, so I'm using the VBA. Doesn't really matter. So I have all of my parameters fit here already from my previous calibration. So I have my gamma and lambda and M and H. And I have chi and N already determined. And the only one and nu, of course, is assumed to be 0.2. The only one that I'm going to play around with is H, which is this one. What H does is a higher H stiffens the model. So the model gets a bit stiffer. If I make it very low, the model becomes softer, so more volumetric strain, and the model kind of becomes softer here as well. And you kind of play around and get the fit that you like. And from there, you come back, and after you did this for all of your tests, you plot this up against the initial state parameter. And usually this turns out to be dependent on density and the state, so you fit a line to it. So those H naught and H psi parameters are basically the intercept and the slope of this line. Things to remember, the goal here is not to get the perfect fit by fiddling with all of the parameters for one test. It's very nice if you want to kind of showcase your work, but that's not the goal of calibration. For calibration, you want to have one set of parameters for all of your samples. It means that you're aiming for the kind of the best overall, which includes some compromise on the individual test quality when it comes to calibration. But that's what you need, because when you go to the next step, which is what Alireza is going to show you in a few seconds, you're going to have that one set of parameters. So I always like to do the calibration the way I showed you, and then leave H as the only one that I end up fitting to the data, and then fit a line to that as well. Usually calibration is done based on drain traxial compression tests, and then I like to check it against undrained traxial or simple shear tests if I have them available. Calibrating to undrained and especially simple shear data is possible, but it's a little more troublesome. So with that, I'm going to pass this to Alireza.
Thank you very much, Mason. Just wanted to mention that if anybody has any question, please type in that question box, and at the end of the presentation, we can, between myself and Mason, we try to answer the questions. So now let's take a look at, I prepared a couple of examples, but I think one of them that is more interesting, I will cover it in this webinar. Probably later webinars, we will cover more examples. So the main example that we have today is of a tailing dam, and I will be looking at the deformation and stability analysis that we did on this one. And the tailing material here, the blue one, is the one that we are simulating using Norsand. So this is the initial state, a new layer of embankment, this one, and also the tailings are added to the model. And the assumption in this particular example that I'm presenting here is that the events are fast, and the situation is going to be undrained, especially for that Norsand material. So the blue tailing material that we have here is going to be Norsand and in undrained condition, and we are using that to simulate the behavior of this tailing material. What I will be focusing on is going to be mostly the effect of that initial state parameter that Mason mentioned on the deformation and stability of the dam. So this is one of the more important parameters, and this is the one that is going to indicate that the sand is dense, loose, or medium dense. The rest of the parameters the same. This is the one that is controlling the effect of denseness. So as an example, I'm showing you here the results of undrained triaxial test on the same sample of sand under conditions of other different initial state parameters. So looking at it here, the denser material, the blue one, if you're looking at it in drain triaxial test, the pore water pressure versus axial strain, the pore water pressure generated here at the end of it is lower values, and the looser material, the one that has that initial state parameter plus 0.025, is the one that is actually generating the highest amount of pore water pressure throughout this test. If it was looser than this, if you're looking at the effective stress path, probably that red line, if it was looser, would go complete liquefaction. Now, I'm looking at all these effects in the dam that I mentioned. So if I'm simulating the dam and assuming that the Norsand material or the tailing material, they are on the denser side, so that initial state parameter is negative 0.025. After simulating the model, I'm getting my maximum number of deformation, maximum deformation, 11 centimeter, which is happening in the area that I brought in the new embankment and the new layer of tailings. In terms of distortion and shear bands, I don't see any clear path to failure here, and the dam was stable. And in terms of generation of excess pore water pressure, the maximum number that I calculated here is 228 kPa. If I'm going for a little bit looser material, you're looking at here, the maximum deformation from the 11 centimeter previously is now 48 centimeter. The simulation was unstable. I will show you what I mean by that when I open the model. And you can clearly see the pattern of failure in total displacement contour, and also you can see the shear band through the contours of distortion that I'm showing you here. So this example, because we had higher generation of excess pore water pressure here, this one is 293, we observed that this model with this state, this initial state parameter is failed, it's not stable. Going one step ahead, further than this, if I have even looser material, if my initial state parameter is a positive value, is 0.025, the displacement, the maximum displacement that predicted was 294 centimeters, so close to 3 meters. This is completely unstable. And from the distortion contours, I can see this whole area that we just highlighted here. So this is one shear band area, this is one failure, this is another one happening here. So there are multiple modes of failure happening at the same time for this dam, for this state parameter here. And the pore water pressure, the excess pore water pressure predicted in this case is 394. I'm just going to go up and down these slides so that you see the numbers. So again, 228, 11 centimeter, 293, higher pore water pressure, more displacement, and it is unstable. And for the loosest case, we have the maximum number of maximum predicted excess pore water pressure, and you have a larger deformation. Now, let me just open the model so that you can see what I'm talking about here. So this is one of the models that actually was converged. This is the very initial one. Let me turn off the mesh. And This is the initial state. The next step is going to be the embankment and the new tailing layers coming in. I'm just going to show you the material properties for this one. Right click here, material properties. And these are all the material that I have used in this model. I have a couple of versions of this tailing material. One of them is the more Coulomb equivalent. I will show you that one later. But this one is my more Norsand material, which is undrained, and the strength parameters and all that are defined in here. I'm using that caps opening option because this is undrained case for this one. And when this is done, you run the analysis, looking at the results, looking at it in the interpret. I can actually reference this stage to the second one so that I can show you what is the deformation, additional deformation that we get for adding that layer of tailing and also the embankment. So this is what I was showing you, close to 10, 11 centimeter displacement for this one. And when I opened the model, I didn't get any warning. This is a converged simulation. You can check it in the log file at the very end. So everything is converged in multiple number of iteration and all that. This one took like 2 minutes to complete. Now, let me show you the other one. This is the one that we had it for the looser case. Initial state variable is plus 0.025. Everything is the same except for the material properties, the tailing materials. This is your initial state parameter. Now, if I open this one in the interpret, you can see that my interpret is actually complaining here. It is saying that, okay, the number of iteration exceeded the maximum number of allowable, which was what I defined in my project setting. Convergence may not have been established or the problem is unstable. So you get that warning at the very beginning. So saying that this simulation did not converge, the results are indicating how the simulation is going to fail. And looking at this, again, you can see that these are the contours of distortion, maximum shear strength. You can see failure happening in this area, mostly through the tailing, and it's coming to the embankment material as well. The embankments are all more Coulomb material. And also you can see some of it here as well. Now, looking at the deformation, is a reference again, compared to the initial state, you have close to 3 meters displacement happening in the body of that embankment. Going back to the presentation now. Since we are looking at deformation and stability for this case, I'm plotting here the crest displacement of the dam versus the state parameter. So these are all the simulation that I ran for this example. Different state parameters was considered for the tailing materials, and I ran the simulation. You can see that, okay, there is a clear jump or changing the behavior when the state parameter is more than minus 0.005. From this point forward, the simulation did not converge, and also the predicted displacement are rather high. What I see from this graph is a direct correlation between the crest displacement, initial state parameter, and whether the model converges to a solution or not. When the model doesn't converge to a solution, usually we say that, okay, the results are not that valuable in terms of the actual result that we are calculating as a result of finite element simulation, but they are actually an indication of, okay, what is happening there? What kind of mode of failure you're looking at? So looking at those models in terms of displacement, this one was the one that was stable. You had close to 7 centimeter displacement for the crest. And these two are two of them that they did not converge. This one is giving you 42 centimeter displacement. This one is giving you 2.5 meter displacement at the crest. So this is just a pattern that I'm showing you, that using the Norsand Constitutive model, looking at the deformation pattern, looking at if the simulation is going to converge or not, you can judge if this structure, if this dam is going to be stable or not. Now, taking it one step further, you can run SSR analysis as well. the methodology that I'm presenting here is not actually in the literature, is not studied very well. At the moment, there are work to be done on the subject, but SSR is shear strength reduction method. You're applying a factor to reduce the strength of the material. That shear strength reduction method is not well established for advanced constitutive model like Norsand here, Camclay, or any of these models that they have some sort of hardening, softening in the behavior. We have SSR very well established for the materials for the constitutive model that are elastoperfect plastic or elastobrittle plastic material, like Morculum, General Supran, all those library of material model that we have in RS2, for example. Let me show you one of these, for example, in RS2. So if you go to material properties, strengths, all these library of elastoperfect plastic bond, elastobrittle plastic bond, these are okay for SSR. These are all well documented and all that. All these slight constitutive models, these are all the same family. You can apply the SSR readily on them. Even these anisotropic bunch, you have it covered for them. But the one that are softening, hardening, like the Norsand one here, these are not, the SSR approach is not well established for them. So what I proposed here for this case, in all these advanced material models, there is footprints of friction angle or some sort of strength for the properties. For Norsand and Morculum, we have a one-to-one relationship between that slope of critical state line and the friction angle. So for this specific case, I'm showing you a couple of cases here for different initial state parameter for the Norsand. Let me actually show you the exact file that I have simulated in RS data. So this one, the blue line, the black line, and red line, these are all Norsand materials. So these are Norsand material with different initial state parameters. So this one is 0, this one is the looser material, and this one is the denser one. And all of them, they have that MTC, the slope of critical state line 1.4. And 1.1 from the equation that I presented to you is going to be equivalent to friction angle of 34.58. And looking at the behavior that I have predicted here, this is a triaxial this is drain triaxial test under confinement of 400 kPa. So triaxial test, drain, initial confinement of 400. The peak value of shear is going to be the same for all of these cases. And to prove that even further, let me animate one of these tests. So the one that we have for the denser material, let me animate this one. When I'm animating it, you will see those failure lines, yield surfaces, and all that for all these material. Let me maximize this. So the orange line here is my Morculum line. The blue line at the top is the critical line, critical state line for the denser material. As you can see, these two are the same. So that final state of failure is going to be equivalent between these two constitutive equations. So this equation holds. Now I'm converting my Norsand strength to a Morculum strength, and using this equation, friction angle is going to be 34.58 instead of MTC 1.4. The other thing that I will do here, I'm importing the pore pressure values from the simulation that I did with Norsand Constitutive model, and I'll bring them as an input to my SSR analysis. So to do that, let me show you the example again. So I did all these in here in the SSR folder. Let's look at the one that I have that fails more than everyone else. So this is the looser material. Let's take a look at the model here. Okay, just wanted to mention again, if you have any question, please type in the question box at the end of the presentation. Between myself, Mason, and the team that we have behind the scene, we will try to answer them. So let me just turn off the mesh, turn off the groundwater grid. So this material now is my tailing material, but this one is now more Coulomb with that friction angle that I just mentioned. If you go to the project setting, I am running my SSR analysis. The stress reduction method is activated. And for the groundwater, what I have here, groundwater, I'm defining my pore water pressure in the field using the grid option. And I have brought a couple of these grids that I calculated using the Norsand Constitutive model under different initial state parameter. And in this one, the one that I used, the initial state parameter was 0.025 is assigned to the model. So right click again, just to show you what it is, hydraulic properties. I'm using the grid for that specific initial state parameter that I mentioned. Now, looking at the results for this one, we put it back. So the grid from the Norsand analysis are pasted here, imported here. They established the pore water pressure field in the domain for me. Now I'm running that SSR analysis on this one. Now let's open this one in the interpret. I will look at it when we come back. Let me go back to the presentation. Okay, so this was the methodology that I used. I converted the strengths between these two constitutive models, and I imported my pore water pressure that I predicted very accurately, very nicely with Norsand Constitutive model, and brought it into my SSR analysis. If I'm looking at one of those models that actually converge using Norsand model with the initial state parameter of -0.005, SSR is actually predicting factor of safety 1.03. So even SSR is confirming that this was a stable factor of safety is +1 plus some value. We are looking at maximum shear strain here and displacement here. If it was going to fail under this shear strength reduction, you can see two distinct failure mode. One is this one, and the other one is this one in this domain. Now, if the initial state parameter was 0, this was the case that actually failed, and we didn't get convergency with the Norsand material. Factor of safety predicted for this one is 0.98, less than 1. So the simulation is unstable. And again, you can see two different distinct failure mode for this dam. So one is going through a longer path, the other one is shorter. So one of them is mostly going through the tailing actually. The other one is going through the tailing for like more 50% of the path, and the rest of it is going through the embankments. The one that was the loosest, and we predicted close to 3 meters of displacement for this one, for the crest. This was the most unstable. The factor of safety for this one is 0.71, and I can see multiple modes of failure happening for this one. One is this one, the other one is happening here, coming through the middle, and the last one is this one going the longest one, the longest span of the failure. Now, this is between the SSR and the Norsand regular simulation. They are confirming each other. To take it one step further, I did the simulation again in slide 2 as well. The slide 2 is our limit equilibrium method analysis tool. And latest addition that we had to it, we have multimodal optimization, and it can actually capture multiple modes of failure in the domain, so that later on, if you are going to monitor your structure, your slope, you're aware that, okay, what locations, what failure mechanism I have to be watching, and which position I will need to monitor in terms of stability. So the slide also is giving me multiple modes of failure. These are very similar to what I predicted in RS2 as well, but let me show you the files as well. So this one's the one that the initial state parameter was 0.025, and the factor of safety predicted with SSR is 0.71. The same model, I ran it in a slide, and it's this file. Again, All the strength properties are the same. The tailing material, then go to this one and turn off the grids. Okay, so the grids are representing that pore water pressure here, equivalent to what we had in RS2. And I tried different scenarios, different search algorithm on this, so that we can take a look at the results at the end of it. So same geometry, same pore water pressure grid coming from that Norsand analysis with initial state parameter of 0.025. Now let's take a look at the results of this one. Again, in a slide, it's better to run multiple scenarios, different search algorithm, different setting for the model. The one that I narrowed down at the end of my simulation is this one. So it's giving me 3 modes of failure. And I'm just gonna show you what I see equivalent to this in RS2 as well. So this one is the most critical one. Let me right click on this one, copy this one. I'll bring it to RS2 and I say edit, paste from slide. And you can see that, okay, the contours of distortion or the shear band that I had in RS2 are perfectly matching from what I see from a slide. So that's my most critical failure mode in this case. If I go higher values of SRF, I can see other modes of failure as well. Let me go further. You can see that, okay, this is the other one generated here. Let me go in the slide. I actually have it here as well. I'll go copy this one and bring it here. If I say edit, paste, this is the second failure mechanism. And okay, let me go back to my RS2. If I go further ahead, you can see that the other modes of failure almost very close SRF values. They are actually appearing here as well. So this is another one appearing here. We go one further ahead. Yeah, this one. We actually go back. So I don't see the other one. And this is the last one. This is the one that is actually greater than these other 2 values, but it's still another critical slip surface. I'll bring this one, edit, paste it. This is that last one. Just again, confirming what we saw in finite element using Norsand, finite element using SSR, and also confirming it with the slide for slope stability. There are so many tools available to you. You can mix and match between them. And when all these tools are actually pointing to the same direction, pointing the same failure, same displacement pattern, same failure mechanism, you can be sure that, okay, I did my simulation correctly and I can put it in my report. One of the things that is a little bit different between slide and RS2 here, for example, is the factors of safety. And that, in my opinion, is that because in RS2, what I have used, I'm actually using all these material properties of stiffnesses, dilation angle, and all these are defined for different materials. So if you want one-to-one comparison, we have in the help manual between the slide and RS2, these values, the default values. If you want to have very close values for factors of safety, you can use those values. But if these values are deviating from that, usually in my experience, RS2 is predicting the factors of safety a little bit lower. But in this case, the other aspect is that the failure mechanisms are so complex. It is going a little bit concave, convex. The shape of the slip surface is very complex. And going from convex to concave in a slide in limited equilibrium is not going to be as easy. But RS2 and finite element, they don't have issue with that. So that is also a factor that is actually increasing that factor of safety a little bit in the slide. But other than that, let me go back to presentation again. You can see that all these simulation that I presented to you guys, they are confirming each other. Failure modes are the same, factors of failure are very close, and the simulation is done very nicely. And it's in good agreement in all these tools. I had other presentations ready for today, but I will keep them for later on, further webinar that we might have. This one, for example, was completely showing the static liquefaction for this sand material, loose sand material in a undrained footing. And we had more examples for soil and pipeline interaction. We save them for later. Just an announcement, then I will get back to the questions. We have more webinars coming. This is one of them in June, on June 8th. We are talking a statistic and back analysis in slide 2 and slide 3. The slide 3 team and slide 2 team, they will present this one. And if you have any other requests, any other tool, any other subjects, let us know. We will try to arrange those webinars for you as well. Okay, thank you for joining us. Let me bring up the questions, and we will try to address as many as we can.
So the first question is from Stefano. For tailings dams, is it better to use recovered samples in triaxial tests or reconstituted samples for precise modeling parameters? So to get the critical state line, you always need some remolded samples. If you have the luxury of getting undisturbed samples, you should absolutely do that, not only for modeling purposes. They serve a lot of other purposes, including confirming your in situ void ratios. And so you would use a mix. Some of Norsand parameters are not affected by fabric, so they should come out the same from those. Some, such as H, and to some extent chi, the dilatancy parameter, would be affected by the fabric. So you absolutely do want to get those samples if possible to use them. If not, reconstituted samples will do. But it's challenging to get undisturbed samples, and especially if you want to do triaxial tests. So absolutely yes, if you can.
Okay, just to mention that, okay, all these questions, we try to answer as many as we can. If we cannot answer them, we will email you the answer to all these questions. I see another question. How do you compare this model to with hardening soil model from Alireza? Hey, the same name, Mirdamadi. Norsand comparing to hardening soil. Hardening soil, first thing first, there is no state parameter in that one, in hardening soil. And also hardening soil, you cannot do softening behavior with it. And if you would like to simulate static liquefaction, it would be really hard doing it with hardening soil. You can manage to some extent with hardening soil, the small strain stiffness and all that. It's not as straightforward with the Norsand. If you would like to go with hardening soil, the application could be different from what we have with Norsand. I would say it that way.
The next question is, are there any direct correlations with CPT results? There are direct correlations between CPT and the in situ state parameter, and it is an integral part of any, especially in tailings dams analyses. It's an integral part of it. That's the first thing you would do. You would interpret the state parameter in situ. You would deal with the variability of state parameter the same way you would do the characterization of any site. Plus et al. 1992 is currently my favorite method for doing interpretation of the state parameter.
Okay, I'm seeing a couple of questions regarding the example that I showed for the tailing dam. I did not go for the whole stages of construction of the dam. This was only an exaggerated case of one layer coming in. And again, it was kind of exaggerated that everything was undrained and fast. But if you're willing to, it's quite easy. You can stage the whole construction of the dam step by step going up. I just showed you one initial, and I just added one step to it, and I made it kind of dramatic so I can get out of this presentation out of it. But it was clearly speaking of the state parameter and how that state parameter, if the sand is loose, if the tailing is loose, a little bit denser than that, how it's going to affect your stability. I think this is one of the subjects that is actually very interesting to the practitioners.
Another question that's kind of in my field is best estimate of Norsand parameters. This is a question from Ali. Best estimate of Norsand parameters when traxial data on specific soils are not available. So first of all, in most cases, if you are dealing with a project where you can do Norsand modeling, that probably means that there is enough budget to get a couple buckets of soil and run a few traxial tests. It's absolutely worthwhile doing that because it tells you a lot, not only for your modeling again, but about the material you're dealing with. If you absolutely don't know your parameters, then some educated guesses is something you can do. If you're looking at a clean quartz type sand, like Ottawa sand, friction angle is about 30, you can have guesses on other parameters. If you're dealing with tailings, these are angular, they're finer grained, they're very, very variable, so you should absolutely be testing them. If you push me, I'll say, hey, pick a slightly higher friction angle, slightly higher chi, higher slope of critical state line, probably depending on gradation, but you should be testing them. And when you're dealing with a wide range of materials, such as in tailings, you should probably try testing at least 2 different gradations to see what the range may be. That's where you'll find a lot of advantages, improvements to your design. So that $5,000-$10,000 for running additional traxial tests is probably worthwhile.
There's another question regarding the state parameter, and well, there is a significant effect that we showed it already, but how to assign it in the domain and all that. Well, all these parameters that we have in the domain probably is not as accurate as it should be that we assign a constant number for it. But I was just showing a slide here. So this one. So if you have a statistical distribution for those parameters, that would be awesome. Currently, we do not have that for Norsand, but we have the statistical distribution for other different, like more Coulomb friction angular cohesion in RS2 and RS3. We have that available. For that request, I'll put it in the list of requested features. We're going to add something for that in that effect. And there's another one that is asking what kind of simulation that I did here. For the tailing dam, I did coupled, but it's undrained, so there is no time in it. For the foundation, I was actually using complete bioformulation, so it included hydromechanical coupling and also time. And for the pipeline and soil interaction, that was completely dry. But we have all these options in RS2 and RS3, but for this specific case that I showed today was the undrained coupled one. Question, inside RS2, can you plot specific points for a stress pass, for example? We have the option, it's being generated also, the one that I actually showed you in the presentation. These are actually from RS2, but this is not out there in the release version yet. But you can actually go to a specific element and say, okay, that element, give me all the information for a stress pass for it. This is going to be public pretty soon. Okay, Mason, do you see anything else?
There are lots of questions, mostly for you. They're about your model.
Sure, absolutely. I would suggest that we conclude this one at the moment. Then the list of the questions is actually pretty long. You're right. We will get back to you guys. We email you the answer, then we'll take it from there. If you have any further questions, email us. If you have requests for other webinars, we would be happy to present it to you guys. Thank you very much for attending. Thank you, Mason, for joining this stage.